Hi, this is Mrs. Rutchling. Welcome to Chapter 17, Solubility. We're going to look at solubility equilibria, that should sound familiar, equilibria, and the solubility products. Solubility is when the rate of dissolving equals the rate of crystallization. If calcium fluoride solid is put into solution, it will dissolve into the calcium ion and 2 fluoride ions. When no more solid can dissolve, it's saturated, and this is at equilibrium. Just like any other, an equilibrium constant can be written. This one is the solubility constant, and if you see, we have the products here. Notice that the solid is not included, just like other equilibrium expressions you may have written. When you learn first-year chemistry, solubility rules are guidelines, but those are very vague. I want to remind you that even insoluble compounds have a small degree of solubility. Instead of depending on those guidelines, in AP chemistry we use the solubility product and also a solubility. There is one misconception I'd like to talk about. If you increase the surface area, for example, if you're stirring, it doesn't increase the amount that is dissolved at equilibrium, it only speeds up getting to equilibrium. The solubility constant is your equilibrium constant, or sometimes it's called equilibrium product. It has one value at a given temperature. The solubility is the equilibrium position. It is the maximum amount of solute that can be dissolved at a certain volume before the precipitate is formed. It is the number of moles per liter, grams per liter, or sometimes it's given in grams per milliliter. Solubility can be equated to X in these equilibrium problems. It's usually measured in molarity, and it will also vary with the addition of the common ion. The solubility of barium oxalate is 1.3 times 10 to the third molar. We have one cation and one anion, so when it dissociates, there's one of each. When I dissolve a liter of water, I can dissolve 1.3 times 10 to the negative third moles of barium. Because it's a one-to-one relationship, 1.3 times 10 to the negative third moles of oxalate can also dissolve in 1 liter. Let's try a simple problem. What is the maximum amount in grams of barium oxalate that can dissolve in 2.5 liters before a solid occurs? Start with the given. I use the solubility as a conversion factor to get to moles, and then I'll use the molar mass to get to grams. Another example is lead 2 chloride. It is slightly soluble. The solubility is 0.016 moles per liter. This time I'm getting one cation and 2 anions. That means that 0.16 moles of lead 2 can dissolve in 1 liter. The molar solubility is always for the ion with the lowest ratio. Twice as much chloride can dissolve, so I multiply the solubility by 2, and 0.032 moles of chloride can dissolve in 1 liter. What happens if you're given the solubility and you want to calculate the solubility product? We know that there is one lead-2 ion for every molecule, so the concentration of lead-2 will be the same as the solubility. However, there are 2 moles of bromide for every 1 mole of the compound. That means solubility is multiplied by 2. Write the solubility expression, plug in my values, and the solubility product is 4 times 10 to the negative 6th. Try this problem. Molar solubility is given, and AB will separate into A cations and B anions. I have a 1-to-1 ratio, so the KSP will be the molar solubility of A multiplied by the molar solubility of B, and E is the correct answer. Here's what a table of solubility product constant values looks like. Copper 1 bromide has a solubility of 2 times 10 to the negative 4 moles per liter. We want to find the KSP, or solubility product. The solubility is going to tell us how much can dissolve in 1 liter. The solid is not important because that does not play into the equilibrium expression. When I first put the solid into solution, I do not have any ions. Putting the values into the chart, I get the values to put into my equilibrium expression, and I can calculate the KSP. This time, the KSP is given, and I need to calculate the solubility. I want to solve for my solubility. Remember, that is X. Plugging in, I find that the product solubility constant is 3.3 times 10 to the negative third molar. When you want to compare solubilities, there's two situations. One where you're using the KSP values. That can only be used if you have compounds containing the same number of ions. For example, calcium sulfate is going to create 2 ions. Copper 2 carbonate is going to create 2, and silver iodide is going to create 2. Then we can compare our solubilities. The most soluble is the calcium sulfate because it has the largest KSP value, where silver iodide is the lowest. Another situation is when you have the actual solubility values, and that is what needs to be used when you have different numbers of ions. For example, we have copper 2 sulfide, silver sulfide, and bismuth sulfide, and we want to put them in order from greatest to least, so decreasing solubility. We can't use the KSP because they have differing number of ions. We can use, though, the KSP to calculate our solubility. When we do that, we get our values for our solubility. Using those values, we can put them in order. Bismuth sulfide has the largest, so it is the most soluble. Copper 2 sulfide has the smallest value, and it is the least. The common ion effect also comes into play when we're talking about solubility. The solubility of a solid is lower when the solution already contains one of the ions of solid. Why is that? If one of the solids is present, Q will be greater than K, and the reaction will shift to the left, creating more of the reactants. This example, calcium fluoride is being dissolved in a sodium fluoride solution. Putting in the values, we have something here for our 2 fluoride ions. Now we have the values to plug into our equilibrium expression. We substitute in the KSP, solve for our solubility. It ends up being 6.4 times 10 to the negative 8th molar. pH can also affect the solubility because of the common ion effect. In this instance of magnesium hydroxide, a high pH means there are additional hydroxide ions that will shift the equilibrium to the left, having more product that will decrease the solubility. A low pH means increased hydrogen ion. In an acidic solution, the hydroxide is going to react with the hydrogen ion to create water. This, in effect, removes or decreases the hydroxide ion concentration, and the reaction will shift to the right. The solubility will be increased. Silver phosphate breaks down into 3 silver ions and a phosphate ion. What happens if hydrogen is added? In other words, if it is dissolved in an acid. Because this is a strong conjugate base, or said another way, phosphoric acid is a weak acid, the phosphate will bond with the hydrogen ion to make the phosphoric acid. The equilibrium is going to shift to the right, and solubility increases. What happens if silver chloride is added? Chloride is the conjugate base of hydrochloric acid. Since hydrochloric acid is a strong acid, the chloride is a weak conjugate base and will not react with the hydrogen ion. Silver, however, is also a product. Adding the silver will cause it to shift left because of the common ion effect. To sum up, if a substance has a basic anion, it will become more soluble in acidic solution. If a substance has an acidic cation, it is more soluble in basic solutions. For example, if HX is a weak acid, we have a strong conjugate base. The salt, a metal, and that conjugate base will show increased solubility in acidic solution. For example, lead 2 fluoride in acidic solution will be more soluble because the hydrogen ion will attach to the fluoride ion, shifting the equilibrium to the right. If I have lead 2 iodide, hydroiodic acid is a strong acid, and so the iodide will not attract the hydrogen, and it will be unaffected by a change in pH.